Excellent. Okay. So everyone, thank you very much. はじめまして、デイビッド・ベネットです。いよいよ最後のプレゼンテーションですよね。多分皆さんお疲れになっていると思いますので、なるべく、あと、今朝のキーノートでいろいろジムもカバーされましたので、ちょっとなるべく短くしようと思っています。あと、申し訳ないんですけれども、英語で日本語でどっちにしようか迷ってたんですけれども、この内容だったらちょっと自信がなくて英語で話させてください。皆さん、ゆっくり聞いて分かんなかったらちょっと後で日本語の質問でも構いませんのでよろしくお願いします。Anyways, thank you for the nice introduction. I think they covered most of it, but I've spent quite most of my career in IT, PC, and actually a lot of it in Japan as well. So I think it was covered in the introduction. So I won't spend too much time here. What I would like to do is tell you a little bit about Tenstorrent. I know we covered some of it in the keynote this morning, but I want to talk a little bit about today, what we are, what we do, and why we're here talking about RISC-V today. So Tenstorrent, we've been around since 2016. We're based in North America, Toronto, Canada, but with offices in Tokyo, Toronto, Sunnyvale, Austin, Belgrade in Serbia, and Bangalore in India. We build the most innovative AI products, and we have one mission: inference, training, CNN, LLMs, NLPs, so vision or language, all on the same chip, same software stack. We believe that's one of our core advantages and one of the ways that we can compete against our competitors. We'll talk a little bit about the kind of software stack we have, but we try and give our customers the ability to run any machine learning model they want, and also the ability to program at the base metal itself. At the same time, as part of our efforts with AI, we've created the world's highest performing RISC-V CPU technology in the world, and we'll talk a little bit about that and expand on what Jim talked about this morning. And again, our CEO gave the keynote this morning, Jim Keller, and we've assembled a team of CPU engineers and AI architects from around the world. So why is an AI company talking about RISC-V? So this is the slide I want to talk a little bit about what we're doing. So AI is at the heart, or RISC-V is at the heart of everything we do. So if you look at today in our architecture, I'll talk a little bit about the roadmap, but in our AI accelerator today, inside our Tensix cores, which is the AI accelerator cores, actually we have 5, we call them baby RISC, but we've got 5 small RISC processors inside that are doing the calculations. This is a very different approach than a GPU when it comes to AI. So this kind of programmability and functionality allows each of those Tensix cores to do data movement, to do simple math, and to accelerate the machine learning model. And that's what we have today. As we move forward, that's where it gets a little more interesting. So the next generation part, which we're taping out this year, Blackwell, actually adds on, in addition to all of the little baby RISCs inside of all of those T's, those Tensix cores, we've added 2 rows of RISC-V cores. And our belief is that the combination of general compute and AI acceleration is going to become more and more important. So this is our first step into that. If we start to look outwards more into the future, that's where the design, our own design of our RISC-V CPU and our AI come together, using chiplets, but come together in a very large what we're calling our Grendel processor, which will combine RISC-V and our AI together to perform different kinds of heterogeneous high-performance computing. So this is our plan, RISC-V today and through the next couple of years. We talked a little bit about our team, but it's not only, we've assembled a number of people from around the world with different skill sets. And I think if we look at our CPU team, one name I want to call out, we've got people from Apple, from AMD, from Intel, from NVIDIA, people that have worked in the industry and have a history of delivering high-performance CPUs. One of the newest members of our team actually is here came here from Japan, originally at NEC. He then went to ARM, and Yasuishi has joined us this year at Tenstorrent in America. So a little bit about how Tenstorrent, we go to market. So if you look at our RISC-V, as I said, we've developed this high-performance RISC-V CPU as almost a companion chip to our AI. But again, our plan is not to go and create our own RISC-V CPU. We want to use that technology together with our AI processor. However, once we've announced and we've presented to the world what we're doing in RISC-V, we've had a lot of inbound interest from companies around the world asking us if they can use this technology. So for RISC-V, we are offering our technology in IP or in chiplets, and we'll talk a little bit more about that. When it comes to AI, it's across the board. We offer our AI technology in IP, in chiplets. We produce and manufacture our own chip, which goes into cards, which then goes into systems, and then goes into the cloud. And we've built that all out. It's available today for customers to buy, purchase, and use. So this was covered a little bit this morning. This is our AI roadmap. So if you look at the first two, Grayscale and Wormhole, these are out today. I think it was mentioned in the keynote this morning. Things get interesting in the middle in 2023. So Blackhole, the chip that we're taping out this year, it adds that row of RISC-V CPUs. Now what's interesting about AI and machine learning models, if you look at the models that run today, even on GPU or some of the accelerators, many of those operations are still leaving the accelerator, leaving GPU, going through the memory, going through the host, and being run on the CPU. Our belief is that as much of that can be done inside the same silicon, you'll obviously see the benefit from that acceleration. On top of that, when we have the RISC-V cores there in the same product, we believe that we'll be able to offload some of the things that the host is doing, potentially most of the host's work, and keep that within the silicon. That's why we call it a standalone machine learning computer. So we start with our Grayscale product, which has the mini baby RISC-Vs inside of all the 10.6 cores. We add our Ethernet fabric to create a very big scale out and connect, chip to chip, card to card, server to server in a large array of devices that are seen as a single device by the compiler. And then in the generation that we're taping out with Blackhole, we add the RISC-V functionality, which we believe takes even more and puts it inside of our product. If we go to the far right, this is where we're driving towards. The future of compute is big AI acceleration and big general compute combined together. So starting in 2024 with our chiplet design, our goal is to be able to offer the flexibility to combine the amount of CPU that you need with the amount of AI that you need. And depending on your workload or depending on your company or your vertical, that could change. So we're going to use chiplets to provide the best solution that's optimized for the workload that you need. So why AI needs both RISC-V cores and AI accelerators? So if you look at the 10.6 cores, we discussed the AI acceleration cores. Really good at vector calculations, really good at matrix arithmetic, large data sets. If you look at what CPU cores are ideal for, conditionality, traditional math, high performance, and robust programmability. When you merge these 10.6 cores and these CPU cores on the same die, you lower the latency, boost utilization, and increases your ML performance. So we believe that ML developers of today and of the future need both the CPU and AI cores to build dynamic models of the future that are not possible today because of some of these limitations. I think this was touched on a little bit, but if you look at, this is our upcoming Blackhole processor. We've got our AI 10.6 cores and we've got our RISC-V CPU cores. We can do some really interesting things because these cores are able to talk to each other. The compute that's required to be done on the AI 10.6 cores can be grouped and put on the AI accelerators. The operations and the compute that is better benefited by a RISC-V by a CPU can be put on our RISC-V cores. And as that data is calculated and moved around the chip, it talks to each other, gives the results, and that data flow architecture that we've created, you can then take the operations that are designed better for the CPU and better for the AI accelerators and drive them through the chip to produce a result and send it over to the next chip. So we believe this kind of integration, especially if we look at the startup landscape today, there's a number of companies that are doing AI acceleration, and there's a number of companies that are doing RISC-V compute. We're one of the only companies that are doing both, and we think this provides us with a distinct advantage. This is an example of when we start to look at our future designs with chiplets. As you can see here, this is sort of a rather large example, but we're showing how you can take a big CPU chiplet and combine it in different ways. You can combine, depending on how much AI acceleration you need, you can put AI accelerators on. And we've heard from customers, okay, on the AI acceleration, we want GDDR. We want memory that's not as expensive as HBM. We need to make sure that you have a certain amount of RAM or a certain amount of GDDR in there. On the other hand, we have other customers and companies telling us, no, we would also like HBM. In fact, we have some HPC customers that want both GDDR and HBM. So we believe that as we move into the new age of chiplets, that flexibility to control the amount of compute that we have, to allow customers to choose what kind of memory, what kind of I/O infrastructure, what kind of I/O subsystem they want, that kind of choice is also going to provide an advantage and a differentiation. We talked a little bit about chiplets, but the future of chiplets is simple. If you can reduce the time it takes to tape out a chip, if you can reduce the cost of the tape out, and if you can provide the flexibility, the number of companies that are going to develop their own silicon are going to increase. So we believe that by enabling chiplets and providing some core technologies like AI and CPU, not only is the TAM of this market going to increase, but we think what customers and what companies are going to be able to do with this technology also increases. So this will be something you'll be hearing a lot about Tenstorrent talking about in the next couple of months and over the next year. We talked a little bit about this morning, but our high-performance CPU Ascalon, you can see outside in the demo room. We started with an 8-wide out-of-order decode CPU, so very high performance, and we've created it in a modular fashion that we're able to scale down, and it's very composable. We've had customers that are asking us for, depending on their workload and depending on their application, they're looking at 6-way or 4-way or sometimes a combination of both. Our strategy was start at the top. We believe that it's easier to create a high-performance CPU core and then work your way down rather than going the other way. And we've talked a little bit about the performance that we have seen so far. And this is through cycle-accurate simulation. We've talked already a little bit about this. I think Jim covered it this morning. But this is what our Ascalon processor looks like. We're currently moving along very well. We've just recently had Linux up and running in simulation. And our goal is to have our next stage of the RTL complete by the end of the year. So how have customers been responding? So we're currently offering AI IP, our AI hardware, and our RISC-V IP in various stages. Last month, we were proud to announce a partnership with LG that has been made public. We will actually have a number of other announcements coming in the next couple months. We haven't been able to talk about too many of them yet, but what I can tell you is the interest from customers around RISC-V IP is real. The interest around AI obviously is very real right now. But what's interesting is the interest from customers around both is also there. We find that when customers come and talk to us about RISC-V, they very soon are looking at an AI solution. Or if they come and talk to us about AI, they also look at RISC-V. And we think they're very complementary. People want to own their own silicon. They're looking at what companies like Tesla and what Amazon are doing, and they're owning end-to-end, from designing the chip all the way to the software and owning that complete opportunity. And this is something that we're looking as Tenstorrent, we want to help companies achieve this. One example is automotive. So we have the ability, if you look at automotive, there's a number of solutions in automotive that are required. You have ADAS, you have infotainment. So Tenstorrent's able to offer AI and RISC-V together. And we've seen companies like Tesla have effectively used that to own their own technology across the entire automobile. When we look into chiplets, we can reduce the cost while accelerating the time to design. It also provides flexibility. Let's say down the road that you've created a chip and you've created a technology and you need to make some changes. With a chiplet approach, you don't have to then go and redo all the technology. You keep the parts that you need, and then you change the parts that you want to see improvement on. For example, you might not need to change the memory chiplet or the I/O chiplet very often, but you want the latest and greatest CPU, or you want the newest AI chip. With chiplet technology, we're able to reduce the cost, reduce time to market, and provide flexibility in making changes at a fairly rapid pace. Automotive companies have sort of seen what Tesla is doing, and they do want to own their own silicon, and they're coming to us to help them develop that, whether it be AI or RISC-V. Power consumption is critical in an automobile, and Tenstorrent AI technology scales from milliwatt to megawatt, and that's something that our customers are looking for, and one of the reasons why you've seen some of the companies already jump on board with Tenstorrent. So we haven't talked too much about this, but we talked about having a bare metal stack as part of our AI offering. So at Tenstorrent, we offer 2 entry points into our software stack. Many customers want to take a machine learning model and just run it. They just want to take a model, run it, combine a model, make sure it works. We've had a number of customers come to us and say, okay, we see what you've done in the architecture. We see the programmability that you provided, and we want to take control. So we want a bare metal stack, similar to what CUDA is doing, but we want something that's open and something that we can go and program. So we've created something called Buddha-M, which is our version of kind of similar to CUDA, which provides bare metal access to our hardware and your own ability to go program those 5 little baby cores within inside those Tensix. So if you look at our Grayscale product, we've got 120 Tensix cores, and within each of those cores, you've got 5 baby RISCs there. So when you start looking at that's a huge number of cores that you're then able to program and leverage to either optimize your machine learning model or to do something that's not a traditional machine learning application. So what are we offering? How are we, looking at what CUDA is doing, how are we different? So Buddha-M advantages, we believe, are advantages over CUDA. So the kernels are pure C++ with APIs, so very easy to program and understand. Decoupled data movement and compute, optimize compute and data movement separately, meaning that if we look inside those cores, we have functionality designed to move the data around, then do the math and control. You can control, in those 5 baby RISCs, you can control every part of that operation. And different cores can run with different kernels with pipelines connecting them. And it gives you direct access to the SRAM and the DRAM. All of this is open. The hardware map is available, and we're going to be open sourcing this later this year and invite the general public to come and use it and try it out. So we talked a lot about why we're using RISC-V. I think most of you know it here, but our customers are saying when they come to us, what are the things that they're looking for? With RISC-V, fully customizable, full ownership. Whether it's IP, whether it's co-designing with us, whether it's purchasing the chiplets, we provide the ability for customers to own their own technology. For applications like AI is a good example. If you need specific data types, if you need to make changes to the ISA, or if you need to make specific optimizations that other CPU vendors won't allow, we will allow that. We can help you do that. We can give you the ability to go do that yourselves. As I said, you can optimize performance for specific workloads if there's something you want to drive. Again, automotive is a great example. You know exactly what model you're going to run. You just want to optimize it as much as you can. This is something that, again, RISC-V and having an open architecture like we do with our AI is a good combination. And obviously, no crazy license restrictions, a lot of flexibility there. We think the flexibility of RISC-V with the flexibility of chiplets, frankly, with the flexibility of a startup, is a winning combination. All right, thank you very much for your time today. Appreciate it.
Thank you, David. So now it's open for the discussion. So
thank you for the interesting presentation. So I have 2 questions. One is the data format.
Yep.
Do you support FP64 in AI chiplet? And also, do you support INT8, FP16, FP8 in CPU chiplet?
So great question. So in our AI today, we do not support FP64. So in our AI chips today, we do FP32, 16, BFP8, BFP4, all the low precision floating point data types that are required. However, if you do have requirements around FP64, because of the way that we've integrated RISC-V CPUs, we do have options. For instance, if we look at the amount of FP64 that's required in AI machine learning models of today, they're not that many. Frankly, the trend is moving towards more low precision. But even if it's not in the AI accelerator itself, you can offload that to the RISC-V cores that we've provided, for instance, in Blackhole. So we do have at least some flexibility and optionality there. Inside our CPU, I can't answer for sure. I don't think so. No, I don't believe so. But again, if you look at our implementation of what we're doing with our processor, we're putting our RISC-V core together with our AI cores. So typically, if something's required for low precision data types, it'll be handled on the AI side.
Okay, next question is, could you show me the slide, maybe 11 or something like that, that shows that the two chiplet, AI chiplet with the CPU chiplet?
Sure.
多分日本語でも OK ですよ。
いや今十分今英語で。
どちらでも。
どちらでもです。11ですか
Maybe next one? No. Okay. So do you have an interface between the two memory controllers? It looks you have a die-to-die interface between the memory controller.
I'm not the right person. I believe so. Yes. If I recall, we've got on both sides and die-to-die and then communication between the memory. Yes.
Okay. Thank you.
So given the popularity of ChatGPT these days, I think the ownership of the GPU became very expensive. So as you talked about the possibility of having your solutions becoming more customizable and fitable to those applications, do you think you have a way of proving that your hardware can be better than NVIDIA GPU, for example, for the large language model ChatGPT-4?
Sure. So I stayed away from focusing too much on AI today. I kind of tried to focus more on what we're doing in the RISC-V space. But absolutely, we think in the AI space, one of our advantages, we have a few advantages, but one of them will be cost performance versus what NVIDIA is doing. So if you look at what the GPUs are doing today, they're using typically HBM memory, which is great, but quite expensive. And there's some penalties in terms of latency that we believe there. If we look at the way we've designed our architecture, one, we have near memory compute, and we're using something like GDDR, which is we believe significantly more cost efficient, right? So if you look at our solutions today, not in the future, not customizable, today, right now, we can offer a significant advantage when you're doing big training or you're doing big generative inference. We provide a significant cost performance improvement versus what our competitors can do because some of the choices we've made in commodity hardware that's cheaper, the architecture that we've done that can overcome some of the differences of not having HBM, and that's something actually where we perform quite well. So if you look at the customers that are evaluating us today, the bigger the workload or the bigger the training or the more GPUs they've used or the more accelerators they need, that's actually the more where Tenstorrent shines because we offer the more compute you need, the more cost performance advantages you'll see using Tenstorrent.
Okay, so following question is, unlike the small automobile or other applications, data center application for the large language model requires a bigger collection of GPUs or server designs, sometimes more than thousands of servers. So do you think the Tenstorrent is ready to make those type of big scale server solutions to compete with NVIDIA?
Sure. So I think there's two things to look at. Oh, there's no screen here. So if you look at our roadmap, our current generation wormhole, so we've designed it with sort of an Ethernet fabric that's around it. The whole point of designing that is it's basically a scale out. It's a scale out computer. So what you can do is using the Ethernet mesh, you can connect again chip to chip, card to card, server to server, and you connect in what's seen by the compiler as a single device. So what that means is if you have the need for extremely large training or extremely large generative inference, you can scale out. And by the fabric that we're using to scale out, you don't need expensive latency-inducing NVLink switches or Mellanox switches in between. You can connect them all together, kind of like in its own sort of mesh. Long answer to a short question, absolutely. So if we look at the interest that we're seeing from our customers today, it's precisely that we can provide that sort of scale out is where we're seeing a lot of interest. You get a cost performance, you remove some of the latency and additional cost adders like switches, and that's something, frankly, again, where we can show a pretty significant advantage versus the competition. Thanks, Peter.
Hi. 他に more questions?
Okay.
日本語で質問させていただきます。 最近が話題になっているのは、チャット GPT の話で、聞きたいんですけれども、GTP、1回で、トレーニングというか、大規模の訓練っていうか、数ヶ月かかるという話をよく、RISC-V って、それに、要は、チャット GPT のトレーニングに対応する技術とか、そういうふうな考え方、やっぱりその時間が、トレーニングの時間が短縮しなきゃいけないというふうな話になるはずだと思うんですけれども、RISC-V をこういった分野でどういうふうに活用していく、どういうふうに。
そうですよね。今のモデルですと、例えば、弊社が今作ろうと考えているのは Grendo、そういうAI と CPU をくっついたチップなんですけれども、そんなに変わりがないかもしれないですね。多少あると思います。今、さっきちょっと申し上げたように、今のモデルでも、GPU であろうか、Accelerator でも、結構そういう CPU のオペレーションが、だいたい一つのモデルに 30%、40% 実はあるんですよ。ということは、GPU でも Accelerator でも使ってないんですよね。結局 CPU に行って、コンピュートして戻ってくるわけ。でそれ RISC-V も同じ AI とくっつくと、確かにその同じシリコン、同じパッケージの中で計算ができるので多少速くなる。それよりも、弊社のAI のチップが、例えばそういう何ヶ月を半分にするとか、3分にするとか、それはもう実際今できるんですね。それは今の話。ただ将来の可能性が非常にあるとも高いとも。なぜかというと、AI のモデルの特徴がもうすぐ変わるんですよね。今のモデルはたまたま GPU、たまたまという言い方なんですけれども、highly parallelized の GPU が結構パフォーマンスが出るんですけれども、次のモデル、新しいモデルがそうとも限らないんですよね。もしかして次のモデルが、CPU の方が快適とかエフィシェントになる可能性があるので、割とそういうエフィシェントのハードウェアを作っておかないと、フレキシビリティがあるハードウェアを作っておかないと、次のモデルはどうなるのか予想できないんですよ。誰も予想できない。なので、テンストレントのミッションが、じゃあ、モデルは必ずこうなるとかではなく、今のモデルを見て、そのハードウェアに作るんではなく、まずフレキシビリティがあるハードウェアで、モデルがどの方向に行っても、ちゃんと対応できるハードウェアを今作る概念なんですけれども、その中では確かに、General Compute RISC-V みたいな、CPU が、もしかして、フューチャーのモデルにも結構効くんじゃないかな、エフィシェンシーが出てくるんじゃないかなってやっぱり予想してます。But no one knows.
Thank you.
You're welcome.
日本語でありがとうございました。今日最後までで、やっと横綱の CPU が出てきたんで、安心しました。一個だけ質問です。この横綱 CPU の TDP は何ワット想定されてますか？
何ワットは、まだごめんなさい、何とも言えないです。ちゃんと、なんて言えばいいのかな。弊社、IP では、かなり configurable なので、結構それなりのお客さんが決めることはできるんですね。弊社が考えている Grendel というその AI と CPU をくっついて、かなりそれなりのパフォーマンス、高い高パフォーマンスが、モデル、ハイパフォーマンスの、なんていうかな、CPU と言ってるのかな、Accelerator と言ってるのかわからないですけど、なるんですけれども、なんていうのかな。正式に発表されてないんですが、パッケージをちゃんと考えて、今のサーバーとかのシステムをちゃんと考えているっていうことを言っていいのかな。なので、そういうちょっと変な、リアリスティックではない数字にはならないんですけれども、多分ここまでしか今のところ話せないと思うんですけれども、ちゃんとパッケージもTDP もパワーも考えておりますので、また発表できるときはさせてください。ご清聴ありがとうございます。Thank you very much.
ありがとうございました。